In this segment, to wrap up our content for this week, I'll walk through the various pieces of the output, how to interpret everything when we run a logistic regression, and then in the last few minutes of this segment, I will provide a checklist of the important things to include when we're writing this up for a presentation or publication. And also, throughout this, I'm going to try to be clear about what to know for this class versus what are things that are more for reference later, because I think there are more of those kinds of things for logistic regression. I think there are certain points where the experts aren't always in agreement about exactly how to do this, so a lot's going to depend on what your industry prefers, your client, or what the reviewer of your manuscript prefers. And I put some of these things in the reference category, so I'll give you places and field to look and websites to try when you are officially doing this analysis for a dissertation or something later. So for now, let's try to get the basics of the concepts and what are the important parts of the output that are more agreed upon and that are kind of standard, and then I'll show you where there are deviations from that. So let's open this up and get started. I had a data set on hand that was gifted to me, actually. So this is totally fictitious. I don't want you to make inferences about heart disease or medical things from this, but I'm treating it like it's real so that we can get into it, try to think through things in a contextualized way. So this is going to be important for comps, and that is to take even a fictitious scenario and be able to think it through in its context. So we're going to talk about it like it's real, okay? Like we have prior in this class. So we have a DV that is binary, of course, and it's coded 0, 1, and our readers by default are going to assume that the 0 means the absence of something, if indeed that framework lends itself to our study. Sometimes there are two categories and one doesn't indicate the absence or presence of something. But in this case, it makes sense to just say that 0 is no heart disease and 1 is that we are diagnosed with heart disease. And then we have a couple of predictors. One is the person's age, and that's just easy continuous variable. And the other is blood type, and I've simplified this one to a 0, 1 as well. 0 means you don't have type O blood. That means you have A or B or AB. And then 1 is that you have type O. And the reason I selected this is to try to keep it realistic, at least at the time of this recording. There is evidence suggesting that type O is a preventative factor for heart disease. So we expect that people who have type O will get heart disease less often, all else constant. Now, don't freak out if you have type A blood or B or whatever, because there are many other factors that also contribute to this. But the blood type is one that unfortunately is showing some prediction, and it's one we don't have control over, so it is a bummer. So that means it's maybe more important. Okay, so I'm just putting some context around this. Maybe it's even more important as people age for them to be careful if they have type A or B blood. And maybe for those people, it may be more important to be considerate of diet and stress. I'm just making, kind of contextualizing this and taking some creative liberty, I guess. And by the way, I want to take this moment to say that everything we can do in OLS on the predictor side, we can also do in logistic regression. And I'll tell you what I mean by that. Dummy coding. So we could have made these blood types into more categories. Type A blood, type B blood, type AB blood, type O. We could have made all those categories and then dummy coded, and that would be totally fine. We can also do contrast coding that we've learned. We could do a sequential regression where we have a bunch of control variables, and then we have the second block, third block. We could also do a moderation. So create an interaction You have main effects and interactions. We could do that as well, just like we do in OLS. And in fact, for the assignment for this week, it will be a logistic regression that one of the predictors is a moderation. So just know that all that can be done, but I wanted to show you a simple case, and we don't have much more time in this class, so I didn't want to walk through all of those kinds of examples, but I'll let you extrapolate those. And by the way, logistic regression is something that I don't see too much in our literature. Sometimes it's there, and in fact, I put online a resource for you. It's a study that used this method, and so you can use it as a template to write up the results and make sure you're not missing anything. But I must say that in industry, there are some important questions that people want answered that will use this. And so for those cases, if you're going into industry, you may want to dig a little bit deeper and do more research on your own. Check out my any reference materials that I have so that you can do this analysis the best that you can and interpret the data most accurately. So let's move on here to the first thing we want to do is call up the null model. A null model is our baseline to which we will compare all other proposed models. In this case, we just have one. We're going to add two predictors. So we're going to compare the model with the two predictors against the baseline or the null, the one with no predictors. And remember, our best guess in the absence of any predictor information is whichever value that occurs most often in that column where we have the DV sitting in our database. So that's just the mode of the DV. So in this case, I showed you in this comment, by the way, some code. The package plier has a nice easy count option for us, and so we don't do a lot of like data cleaning, data manipulation in this class, but there are some times when some of these things are helpful. So when we did the count and I ran this code, we see that there are 43 cases of heart disease out of the 100 people in the sample. And then there are 57 no's, 57 zeros. All right. So remember, the odds is just the proportion of people who got the thing to people who didn't get the thing. So in this case, it's going to be 43 over 57. And that information is called up by this line of code, by the way. And it's down here. This is the odds. And so if we did a 43 divided by 57, this is what we get, 0.7 something. And this could be above 1, which means there are more ones in the data sets than zeros. But in this case, it was the opposite, more zeros than ones. And so we have this as a decimal. So I gave you this information over here. This is the odds for the null model. So for every given case in the data set, we're going to assume they did not get heart disease. And we'll be right 57% of the time. And wrong 43%. So the goal is, can we improve this prediction? Can we be right more than 57% of the time? That's the goal. Okay, so that's our baseline model. We're right 57% of the time, and so we're going to compare our proposed model to that, and hopefully we will be right more of the time. That is the big goal. Now, for these coefficients, this is not very helpful. This is just the intercept, by the way, and this is the number that would go into that predicted value of the DV. Remember, is that proportion with the natural log, and then the exponents, the regression equation is in the exponents, and that's where this would go, in the exponent, and we will have no predictors, so it would just be this estimate here, intercept, plus 0, because no predictors, and then adding error in, which I don't think I put in that equation. But remember, I said error is always there, and it's just kind of a foregone conclusion. Sadly, we don't usually put it there, even though we probably should. And then these things aren't as helpful. Don't worry about these, because this is just the null model. What we're doing with the null model is we're simply establishing our baseline. This line of code is a GLM function, and then or command, I should say. And then the formula is just the dv itself, and then we have the binomial family. We're just telling the R that basically this is going to be a binary outcome, and it's going to be different than the other ones that we've done. Now the AIC is an index of fit. And so know that it's one way to index fit. And the smaller this is, the better the fit. So we expect that when we enter more predictors that are good ones, that this is going to reduce. It's going to diminish. And that's all you need to know about this Akaikai information criteria. I'm not sure how to say that name, but there's more information in field. So this is one of those things that you may want to report that. The AIC for the null model and then for all your proposed models, if your reviewer asks you to. But that's not something I would do by default necessarily. Well, maybe you can throw it in. But much more important would be the chi-square difference test, which we'll get into. Now, second, we're going to create our hypothesized model. So we're trying to do better than the null. And so we are going to regress our DV, which is the cardiac heart disease, on age and blood type. And I named this type O because that is what's in the 1 category, is type O. And then family binomial, same thing. And then we're going to ask for the EXPBs, which I'll get into here in a second, down here. We'll talk about that down here. All right, so the coefficients for this are different. They are interpreted differently than in OLS, and in fact, their actual values aren't as important as seeing if they're significant or not, and then we'll get into the effect sizes and how big the change we would expect based on 1 unit increase in our predictor. What do we expect that likelihood to change of falling into the 1 category? By how much should we expect that to change? All that we'll get into. But a lot of times reviewers and people want to see these numbers and their Z value instead of a T or an F value. We have a Z value for these, and that's called Wald's Z. It's just a different statistic, and it's used for this kind of estimation method, this kind of outcome, this binary. And then we have the probability of significance here. And so both of our predictors are significant, so that's what you'd want to report. All right, so that's pretty straightforward. Again, don't interpret these. It's not necessary for this class that these are interpreted, but these would go into that predicted value of the DV, like I mentioned before, with that natural log, that E number, and then the exponent. All these would go into there. So let's move down now and talk about these 2 numbers briefly. We're going to get more into chi-square deviance test below. But these are the chi-square values for the null model and then for the proposed model. And I'm not sure why it's called residual deviance, but this is the chi-square value that is a fit index for the proposed model, and then this is the fit index for the null. And like the AIC fit index, as we add more predictors that are good ones to the model, we're going to see that value decrease. And then the DF in this case is just simply n-1 because there are no predictors. So it's the formula would be n minus k minus 1. So we have n minus 0 minus 1 in this case, and then n minus 2 minus 1 for 97 for the proposed model. And then the AIC value is also decreased. My understanding is the AIC is a good fit index for when you want to control for the number of predictors in the model, and so it provides an adjustment for that, a correction for that. So I'm not exactly sure about AIC, but what we're going to do instead is look at the chi-square difference. For the next part here, this I wish was not an essential thing to know, but it is actually. Because the odds ratio is a ubiquitous result that people put into journals and presentations whenever they do a logistic regression analysis. And that basically is, we also call it like odds ratio OR, so when you see OR you know what that is, and then also the EXP B in parentheses. So basically the odds ratio is a comparison, it's a proportion of odds, so it's a proportion of fractions, which is annoying. And I wrote it all out here for you, right? So the odds ratio basically is for each predictor. We want to know that predictors not impact on the DV. I don't want to say that because it implies causality, but we want to know the association, the statistical association. It's kind of like a correlation. And the way we do this with a binary outcome is a little more complicated. So we take a 1 unit increase in the predictor. That is the same with OLS and the B weight. Remember, with 1 unit increase in the predictor, what can we expect to happen to that, to the DV? But in this case, it's all about where each given case lands. Which two groups do they land in? All right. So the odds ratio above our line in the numerator, we have the odds ratio after a 1 unit increase in the predictor. So that is how many people landed in category 1, basically, number of ones in the DV, after the 1 unit increase in the predictor over the number of zeros after the 1 unit increase. So remember, odds is probability of event over probability of non-event. Okay, so ones, how many ones were there after the 1 unit increase in the predictor, and then how many zeros over. And so that's just the numerator of the odds ratio. And then the denominator of the odds ratio is prior to that 1 unit increase in the predictor, how many ones over how many zeros. Okay, so the odds ratio, know what that is. So basically it's the number of people landing in or cases landing in category 1 over the cases landing in category 0, group 0, and then divided by the original odds. The original odds. So if that odds ratio is 1, okay, there is a 50-50 chance of landing in category 1 for each 1 unit increase in the predictor. So if we had a predictor with an OR of 1, then that's not a good predictor. So we would probably throw it out because it's not helping us. Now, if we have an OR of above 1, so it's not near 1, it's not 1, but it's greater than 1 by hopefully a substantial amount or some amount, then we know that the predictor, as we increase on it, it's going to increase the probability, the likelihood of the case landing in category 1. So it's going to increase the likelihood of the event that we're looking at, in this case heart disease. Now, if that OR is less than 1, so it's a decimal, then we know that increasing the predictor makes landing in category 1 less likely. Okay, so increasing that predictor is going to decrease the odds of landing in category 1. All right, so that you have to know. All right, so for this class, understand what an odds ratio is. Understand that it's 1 unit increase in our predictor. How does that increase or decrease the likelihood of landing in category 1? Okay, it's always about category 1, whatever that is. So know this, and then when you're given some sample output to look at, check out the odds ratio and be able to interpret what that is. So first, we know that it should be obvious, hopefully, that with age, because it's over the value of 1, so it's 1.12 something, that means that as we age, we're more likely to get heart disease. That's just very obvious. all right? And then with type O, it's going to be a little different because remember, it's the 0 is not type O and the 1 is type O. So as we go from 0 to 1 as non-type O to type O, we can expect a decrease in heart disease because it's less than 1, right? So the proper way to articulate this, it gets a little bit wordy. And oh, by the way, this odds ratio is the multiplier by which we can expect the odds of landing in category 1 to increase for each 1 unit increase in the predictor. And so for ORs that are over 1 or greater than 1, that's really easy because all you need to say is for each year increase in age, for example, the odds of getting heart disease are 1.12 times greater. Okay, that's all you need to say for, I forgot my quotation marks here. That's all you need to say for ORs that are more than 1. And this could have been 2.12 times greater. It doesn't matter, or 3 or whatever. However, for this one, if we're going to go by this logic, we would say as, let me think about this. For people with type O blood, the odds of getting heart disease are 0.148 times greater, which doesn't make sense because it's less than, it's like a decrease in odds. I hope that makes sense. It's a decrease in the odds. So if you say 0.14 times greater, you're really talking about a decrease, not an increase. And so let me just be clear. If on an exam you put that, if you just stuck in point, like a number that's lower than 1 or value lower than 1 here, and then just said times greater, that would be fine. It would just be a little confusing for the reader, but I'm sure people have worded it that way, and it would be correct, right? So no deductions for that. But for an OR that is less than 1, this is where logistic regression is kind of confusing. Let's just be honest. But for if it's less than 1, what you would say is the reciprocal of this, and that gets you to the decrease, the amount of decrease. Okay? So this is akin to, by the way, taking that cardiac heart disease and switching the zeros and ones. So we would make 0 heart disease and 1 no heart disease. And then we would run it, and it would be, we would get an OR of 6.71. But without doing all that work, all you need to do is take the reciprocal of this, which is just 1 over 0.14 blah blah. And that was about 6.7. So this tells us that for type O blood, people are way less likely to get heart disease, and it's a greater effect size than even the age, which I don't think is realistic. I don't think the real world data reflects this. So again, this is totally fictitious. But anyway, just so you know that when this OR is less than 1, it just makes the interpretation a little bit more difficult because up here, remember, it's the multiplier by which we can expect the odds of landing in category 1 to increase. It's always increase. So if that increase is 0.5, then that's really a decrease. All right. So that's where it gets a little bit confusing. I hope that it's a little bit clearer. Just keep working with it. In fact, if those of you who would love to play with data, just recode the zeros and ones for that DV and then run it again and see if that OR comes out to be 6.7 for the type O blood. It should do that when we switch the zeros and ones for the DV, but then this age one will change as well. And this should be in the opposite direction again. And we'll get a number that is less than 1. Why is this the case? Big picture. Because we have one variable that's positively related to landing in category 1 that makes it more likely. And then we have one, the other variable in the equation that is working in the opposite direction. It's creating a situation where we are less likely to land in category 1. All right? With the increase in this one. So it's all in how you code it, and it's all in interpreting these ORs and making the important thing is to help it make sense for your reader. help it to make sense for your audience or your client. Okay. So this is the way we'd articulate things. Just going to put quotes here. This is just an example of how you can say what the OR is doing, or what the predictor is doing. All right, let's move on to assessing overall model fit. So we want to know if the overall model fit is better for the proposed model than it is for the null. And that's not really a high bar to clear, quite honestly. But I just want to let you know that you could test several models that are nested. Nested means that you just add predictors one at a time or a few at a time. So you could do all the covariates and test that block. Well, first you would may want to do the null just for completeness. So you have the null model, then all of your covariates, and you find, oh, the covariates create a better fit. And then your focal variables, and then maybe a moderation where you have two of those primary variables and you think they're interacting to predict the likelihood of landing in category 1. Then you would do that and have it in a separate step. And you'd calculate, pardon me, all the chi-squares across those models, and then we'd do a chi-square difference test to see if the blocks are significantly different from each other. It's exactly akin to when we did sequential blocking, remember, all the way back in week 3. So first, let's obtain the chi-square differences between the null and proposed models. That's where we're going to start, and by the way, all of this code is located in field, and so we're just going to create this model chi, which is created from the null deviance and then the model 1 deviance tests. And then oh, by the way, this is a -2 log likelihood, they also call that. And field talks about what that is as well. That's just a fancy way of saying the chi-square value. I just call it the chi-square value. But -2 log likelihood is what it is labeled as in some output. I don't think in our output it's labeled that way, but it is definitely in some other stat programs, so just so you know. And so we're going to calculate the difference between these two models, and it's giving us the probability. So all of this code generates this output. And so the first line is 45 point something, and that is the difference between the two chi-square values from the null model to the deviant, the null model to the proposed model. And remember, the null model is going to have the bigger of the two. So subtract basically, yeah, I think 91 from 136, and that's what you get, 45. And that's located here. And then 2 is the DF. So we asked for the DF difference between the two models. And so the null had none, and the proposed model had 2. So that's why it's just 2 minus 0. And then the associated p-value that specifically associated with that difference in chi-squared is this. And so this tells us that the two predictors added significantly to the prediction of heart disease. That's what this means. Now we could have done 3 models, and I didn't do this, but please feel free if you're nerdy enough / motivated enough, which is always encouraged in this class, to do 3 separate chi-square tests, and or 2, I guess. Compare the null model to the first, to age, see if age predicts significantly over the null, and then add the next variable, which is the blood type, to that, and see if that adds significantly. I'm assuming that they do, simply because each one of them is significant here. So I'm assuming if you did a chi-square test, it would be it would confirm what we already see here. Now, a lot of times reviewers and people in the field like chi-square testing better than simply reporting these z-values. There are apparently some issues with walled z that people have, like statisticians who study this for a living. And so I don't want to get into all that here, but just so you know, this chi-square difference test is helpful. So just know this is, again, things to know. Chi-square difference test is important. It's always for nested models, meaning that every prior model, we're just adding pieces to it. So this doesn't work if we're testing two separate analyses. Like if you had another study where you were testing the probability of getting cancer, for example, and you had all your predictors and then the heart disease one, you couldn't do a chi-square test across those two different things. It just wouldn't make sense. We always need to do nested models. And nested models means that we start with the null usually, or one predictor, and then we add slowly and we build the model, and then we stop adding predictors when they don't give us a significant change in chi-square, basically. So nested models are important, and in this case we have fulfilled that requirement. And so that's what, and by the way, this technique is often done when we do maximum likelihood testing and other kinds, which you'll learn coming up, I think, next quarter, and in psychometrics as well. And I know multi-level modeling also depends on this testing the chi-square difference across these nested models as we add more predictors. All right, now let's obtain the R-square. By the way, the R-square is not the same as OLS. It's not the proportion of explained variability to total like we have seen in the past. But instead, it's all about comparing the proposed model to the null model. And so in that sense, it's exactly the same as all the things we've been talking about. And so know that for logistic regression, there are many different ways to calculate the R-squared, and I don't think the experts are totally agreed on which one to do. So I default to the Nagelkerke, and it's also called some other things in the literature. So this is the problem with challenge. Oh, here it is. Craig and Uller is another term for it. So if it feels like maybe Nagelkerke was a person who first invented this, and then these others came along as well and found the same one, I guess. And same with these, Cox and Snell. These are two people who I think invented this way, and then McFadden, same thing. So they call these pseudo R-squares, which is weird. I'm letting you know how to obtain these R-squares simply because reviewers and clients may want to see them. And know there are other kinds of R-squared, like there are 10 plus kinds for logistic regression. And I'm just showing you the three, like, I think most common ones. So, and know that all of these are simply a type of index. This is all you need to know, a type of index of how well our proposed model improves over the null. Okay, so it's not the proportion of variability anymore. It's more about comparing to the null and the fit. And by the way, I went to all this trouble to do this code for the chi-square test, but this our companion package is really cool. Gives us all these R-squared. Hopefully the clients or the reviewers will want to know one of these three. If not, if it's a different one, you can always Google. But this chi-square difference test is right here. So the log likelihood, it has this value here and the difference between the two, and the difference between the log likelihoods, and then the chi-square that goes with it. So all very nice. That means you don't even have to do all this work up here if you don't want to. So anyway, I might just provide this part on the exam so that you have this right here in front of you. And you would just say the chi-square difference variable is, the difference between the two chi-square values is 45, a point something, and its associated p-value is this with 2 degrees of freedom. That's 2 degrees of freedom difference. Remember, from the 99 to the 97, and that's a difference of 2. All right. Next and last, we want to create a table that provides predictions versus observed values of heart disease. So basically, we want to know, with our two predictors, where were the cases predicted to land versus where they actually landed. And this is going to be sort of like the type 1 and type 2 error, where we have 2 ways to be wrong and 2 ways to be right. It's kind of back to that. So I had some code here. We have to obtain the predicted values with this. So this is how we would do that, and just run these 2 lines and then create a new column called prediction, and it assigns any predicted values that are like equal to or greater than 0.5 into the one category, heart disease, and then the others to the no heart disease. And then add that column to the data. So that's what this is. And then a new table with the table command. So I went through and set things up so that I could finally get to this part. And by the way, you can run all these and see what happens. This is what I'm getting to. So all these steps are necessary, I think, before we can run all of this hot mess down here. So I'm just going to put this on the next page, actually, so it's just neater and nicer to look at. Finally, we want a table that combines all this information. And I used the package G models to get this done, and somebody really did a lot of nice programming in the background to make this happen, so I'm going to use it. So this mess of code creates this beautiful table with the predicted versus the observed heart disease. All right, so across the top here we have the observed DV, the people who landed in the 0 category versus the 1 category. But on the rows we have the predicted values, which are 0s and 1s. And so we want to know the times we were accurate versus inaccurate with our predictive model, I should say, our two predictors comprising the predicted model. All right, let's see here. So this value, let's see, the 9, this represents when we were wrong. One of the times we're wrong, and the other time we're wrong is down here. Okay, so on this diagonal, we were wrong. We were only wrong 16 times. Yay! Out of 100, that is not bad. So, but it is a bummer. Every time we're wrong, in the real world, right, we make wrong decisions about people. So it's not desirable, but it's better than when we were wrong 43 times under the null, right? So we were wrong 9 times, and specifically we were wrong when there was heart disease predicted to happen, but none in reality. So this is 0 here. No heart disease in reality. We observed, this case was observed to have a 0 in the DV column, but yet they got heart disease, right? And so this one is where we said they got it, but they didn't. That is a false positive, and that's not good. Okay, so that's a bummer. False positives suck because we tell people maybe, oh, you're in the high risk category, right? And you know, by the statistical model, you're predicted to get heart disease, and then they didn't. And so may have caused them extra worry, right? Let's go to the other case when we're wrong. So we're wrong here when we said no heart disease, but they actually got it. And so this one we would probably want to keep even lower than this one, ideally, right? Because even though both cases suck to be wrong, in one case we're telling people not to worry, and then they get it. Right, so that's 7 people who had that. They thought they didn't have to worry about anything. They're just carefree in life, and then they got heart disease anyway. Right? So these are the 2 ways to be wrong. So we're wrong 16 times out of 100, but we were correct. So here, the person did not get heart disease in reality, and the model also predicted no heart disease. Right? So that's 48, and then the opposite here, and that is getting heart disease, predicted to get it, and then they did get it, and so that was 36 people. And then we have column totals, row totals. It's so nice and pretty, isn't it? And so I find this actually much easier to explain than the odds ratio. People get this. They understand percentages. Odds ratios don't lend themselves to percentages and just easy explanations. The only reason you have to know it is because it's just this ubiquitous thing that we do in the field, especially in journals. You have to report those lovely EXPBs, odds ratios. But this table I find very helpful. And so I would include this table in any presentation of when we were right with the model, when we were wrong with the model, what percentage were we right versus wrong. So total correct predictions. So we have 36, we were right here, and then we have the 48, we were right here. Add those together, and out of 100, we're right 84% of the time. And that's a big improvement over the 57% we were correct in the null model, right? And so this is something you have to know. Talk about things in terms of percentage of correct predictions under the null versus the proposed, and that's really helpful for people. They get that. It's more intuitive than those ORs, I think. And we don't know if that percentage is statistically significant. That's where you do the chi-square difference tests. That's where you do that work. And that way we know that this percentage is not non-trivial. I'm sorry, I used a double negative. It's not, I'm sorry, I should say it's not trivial. This difference in percentage from 57 to 84 isn't trivial, meaning that it's a good thing. It's a substantial difference, and it is not likely to be due to chance, right? So we have a nice increment in prediction, and it's not due to chance. All right, so is there anything else I wanted to say here? I want to make sure before I wrap up that everything is good. And by the way, I wrote this all out in the comments. A lot of the things I'm saying I'm writing out in the comments here, so you can look at this and at least get a good enough idea of things without listening to this narrative, again and again. Oh, and then finally down here with this table, there are a few other things that are provided in the output, which I really didn't know about actually until, I guess we can put this up a bit. But the chi-square test is done again for us in the G models and the line of code. So it prints out this, and then it's this correction also, and this is used. I didn't know about this actually, so I had to do some Googling. It's an upward bias actually. Correcting on the fly here. It's used to correct for upward bias that's inherent when running a 2x2 for a chi-square. So in this program so far, we haven't really learned, in the stat sequence, you don't learn about a 2x2 chi-square. But basically you have a dichotomous or binary predictor and a binary outcome. Okay, and basically that's what this is. It's running a chi-square test where where a predicted 0 or 1, right, is correlated, or that's our predictor, I should say, and then our DV is the actual. That's how this chi-square is run. And so predicted, did they get it, did they not, versus observed, did they not, and then we get a chi-square value for that. And it's the crosstabs in SPSS. You can do it in R. Also Excel, I think, does these 2x2 chi-square, but I actually didn't know prior to this, so this is a new thing for me, that when we do that kind of 2x2 chi-square, there's some kind of inherent bias that happens that is artifactual. That means it's not wanted, it's not useful, and can happen. So what SPSS, but R puts out here for us is this Yates correction, and this is supposed to be more reliable. So just so you know what this is, I stopped this screencast or paused it and then put this in here to make sure that you know this section is for reference only. And also I stuck in here a link in case you want to know more about this continuity correction. And I learned something new, but this I would put definitely in the category of rabbit trail and reference. All right, so hence this. All right, so that is the end of the outputs. And so now I want to do a wrap up and conclusion. So let's go over this checklist for reporting results of a logistic regression analysis. Like any analysis, state your hypotheses clearly, and how the variables were coded matters so much for this kind of analysis, because the way that you interpret all the output, it all hangs on how that DV was coded. State the overall chi-square value for the final model and for interim models as well, I would say. So make sure that those are reported. Indicate the R-square for the final model that we do. I default to Nagelkirche, but other reviewers may have different opinions about which one to include. Indicate the B weights, or the and the B weights are those estimates in the output. So just so we're clear, what I mean by that is going back to the output here. When I mean when I'm talking about B weights, I mean these estimates right here. So these are the B weights for a logistic regression. Remember, they don't have a lot of interpretive meaning in this case, but be sure to include them because reviewers want to see them. And include their SEs and the Wald Z tests that go with them and the probabilities that go along with those, and the ORs or the EXPBs for each variable. So make sure that all of that is included. Just know that odds ratio or OR is the same thing as the EXPB. Plot and display simple slopes if you have a moderation. And by the way, this is just a star to take you to the notes at the bottom of the slide where I'm just saying that there's going to be an assignment for this week where moderation, the logistic regression that you'll run is a moderation. And so you just use the same R code that you would use, the same way that you would use in a OLS, creating that interaction term is the same thing. So there's nothing different that you really have to do except to use the GLM instead of the LM. And make sure you put family binomial, of course. And then the classification table. So the G models package, all that code that puts out this pretty table with the false positives, the false negatives, so the 2 ways that were wrong, and then the 2 ways that were right, and be able to talk about what was our percentage of being correct, correctly diagnosing, quote unquote, or predicting in the null model versus the proposed model, and how does that look, and talk that through in your presentation with your client or whatever you're doing. All right, well, this concludes, finally. Thank you for your attention. This logistic regression is a little bit more challenging in some ways, but there are a lot of things that are similar as well. And so I look forward to seeing you in class, and we will nail down any areas that need it and make sure everything is clarified. Take care, and I will see you then.